All right, in this video, we're going to talk about section 9.4 dealing with two variances or two standard deviations. And in this video, we'll talk about how to conduct a formal hypothesis test of a claim made about two population standard deviations or variances. Now, this section is a little bit different because we're going to present what they call the F test for testing claims made about two population variances or standard deviations. Now, the F test uses the F distribution. And also, it requires both populations to have normal distributions. Here, this test is going to be very sensitive to departures from normal distributions. So the normality requirement is going to be very strict. Okay. So what I'm going to do is show you, excuse me, our objective and also the notation and give you some of the requirements. Here's our notation. S1 squared is going to be the larger of the two sample variances, and N1 will be the size of the sample with the larger variance. Okay, and then sigma 1 squared will be the variance of the population from which the sample with the larger variance was drawn. And the symbols are the same for the other population. S2 squared, N2, and sigma 2, sigma squared sub 2. Okay, so here those are used for the other sample and the population. All right, so now here are your requirements. The two populations are independent. That means one population has no relationship with the other population. Okay, they're not related in any way. They're independent of each other. Number two, the two samples are from simple random samples, meaning that samples of the same size has an equal chance of being selected. And then number three, each of the two populations must be normally distributed, regardless of their sample sizes. Okay, so here the F test is not robust against departures from normality. So it performs poorly if one or both of the populations have a distribution that is not normal. Okay, the requirement of normal distributions is quite strict for this F test. Okay, so you must have a normal distribution for both of your samples. Now the test statistics on the next page is this. Capital F, which is equal to the quotient of S1 squared and S2 squared. S1 squared is going to be the larger of the two sample variances. Okay, so it's just dividing the larger of the two sample variances by the other sample variance. Okay. Now for the p-value, excuse me, the p-values are going to be automatically provided by technology. And here we're going to use the TI-84 plus calculator. Now, unless technology is available, we can compute the value of the F test statistic with table A-5 to find a range for the p-value. But we're going to use the TI-84 plus calculator to do this. Now for critical values, you can get the critical value if you were using table A-5, but we won't be using that in this video. But let me show you what table A-5 looks like. Looks like this right here. Excuse me. Here we use this table to find the critical value or the critical F value. Now, the top row represents the numerator degrees of freedom, which is, of course, N1 minus 1. That determines the column of table A5. And that's this right here. Here's the column. And then your denominator degrees of freedom, N minus 1, that's here and here. Here's your denominator degrees of freedom on the left and then your numerator degrees of freedom is up here. Okay. And that's going to determine what your critical value is going to be based on those two pieces of information. Now, for a significant level of alpha equal to 0.05, you're going to refer to table A5 and then use the right tail area of 0.025 or 0.05, depending upon the type of test shown below. Now, if you have a two-tailed test, then you'll have to use this table with 0.025 in the right tail. Okay. And the reason being is because 0.025 is 1/2 of 0.5, because it's like 0.5 split in two tails. So 0.025 will be that part for the right tail. Now, if you have a one-tail test, on the next page, you're going to see here that I'm showing you in the textbook, you use the 0.05 in the right tail. And that's only for a one-tail test. Now, fortunately, you will not need to use this table. We're going to be using technology to help us compute our test statistic and the p-value. So we're just going to focus on that. Okay. Now let's talk about the F distribution. Okay, so for two normally distributed populations with equal variances where sigma 1 squared equals sigma 2 squared, the sampling distribution of the test statistic F equaling to S1 squared divided by S2 squared is the F distribution. And there are properties of the F distribution. Number one is that the F distribution is not symmetric, as you can see in this drawing. The values of the F distribution cannot be negative, okay? So it's just non-negative values only for F. The exact shape of the F distribution depends upon the two different types, the two different degrees of freedom for the numerator and the denominator. Okay. On the next page is how to interpret a F test statistic. And if you have two populations really do have equal variances, then the ratio S1 squared divided by S2 squared tends to be close to 1 because S1 squared and S2 squared tend to be close in value. But if the two populations have radically different variances, S1 squared and S2 squared tend to be very different numbers. Because we're stipulating that S1 squared is a larger sample variance, the ratio S1 squared over S2 squared will be a larger number whenever S1 squared and S2 squared are far apart in value. Consequently, a value of F near 1 will be evidence suggesting that sigma 1 squared equals sigma 2 squared, but a larger value of F will be evidence against the conclusion of equality of the population variances. So here, large values of F are evidence against equal variances. Now here's how we use the TI-83 and the 84 plus calculator for hypothesis test. And that's this, the TI-83 plus calculator is designed for that, but we can't use it for confidence intervals for two variances or two standard deviations. Okay, now I'm going to have to beg to differ on this part right here. In order to simplify the hypothesis testing procedure, the method described in this section requires the larger sample variance be designated as S1. But this is not necessary if a TI-83 or 84 plus calculator is used. Either sample can be designated as S1. I'm have to beg to differ on that one because the larger of the two will have to be S1. And then the other one will have to be S2. Okay. There is a reason for that because you're going to get a wrong F-test statistic if S1 is not the larger of the two when you do this in the graphing calculator. Okay, I'll mention that when we do examples of that. All right, number one, you have to press the stat key, then use the right arrow key twice, press that twice to select test. Then you're going to use the down arrow key to select this menu item. This is 2SAMP F-test. That's the one you're going to use, 2SAMP F-test. That's just short for 2-sample F-test. Then number three, for the input entry, you're going to select data. If you have two less than sample data already stored in the calculator, or select stats. More than likely, we're going to be selecting stats because we're going to be getting the summary statistics in these examples. S1, N1, S2 squared, N2 squared. They're going to be known. And if the data was selected in step 3, you'll enter the list names or labels such as L1, L2. If stats were selected, you'll enter those values, S1 squared, N1, S2 squared, N2. Then you're going to select the type of test, or in this case, two-tailed, left-tailed, or right-tailed by selecting the format of the alternative hypothesis. It's either going to be not equal to, or less than, or greater than. Just have to look at your alternative hypothesis. Then go all the way down to calculate, select that, and then you press enter. Okay, and you'll be given not only the F-test statistic, you'll also be given the p-value as well. So let's look at some examples of this. Starting with example 1. It says here, researchers measure skulls from different time periods in an attempt to determine whether interbreeding of cultures occurred. Results are given below. Assume that both samples are independent, simple, random samples from populations having normal distributions. Here we want to use a 0.05 significance level to test the claim that the variation of maximal skull breadths in 4000 BC is the same as the variation in AD 150. Okay, so here's our data set. All right, now I need to look at which one of these standard deviations is greater. Okay, because I want the correct F-test statistic for this. So I have to let S1 be the greater of these two. And in this case, that 5.31 for AD 150 is the one that's greater. Okay, so now S1 is the greater of these two. That's the 5.31. And I need to know what N1 is. For this, N is 30. So N1 will be 30. And S2 will have to be the other standard deviation. That's 5.19. And N2, of course, for the 5.19, that's going to be 30. Don't worry about the means here. That's not used here in this type of problem because we're dealing with two variances or two standard deviations here. So we don't need information about the sample means for each one. Okay, now let's go through that 8-step hypothesis testing procedure. So step number 1 would be the original claim in symbolic form. So we're testing the claim that the variation of maximum skull breadths in 4000 BC is the same as the variation in AD 150. That means the variances are equal to each other. So that means sigma 1 is equal to sigma 2. That's the original claim. Is the same is in symbolic form equal to. And now step number 2 is the opposite of the original claim. or the opposite of equal to will have to be not equal to. So it'd be sigma 1 is not equal to sigma 2. And then step number 3 is writing the null and alternative hypothesis. Well, the null has the equal sign in it, so that means sigma 1 equals sigma 2. And that's also the claim. So I'm going to write the word claim in parentheses. The alternative has to not equal to, so it'll be sigma 1 not equal to sigma 2. All right. Now, step number 4 is the level of significance. The alpha level in this case is 0.05. That's given to us in that problem. And now step number 5 is this. Here we're going to use a TI-84 plus calculator to find out what F is going to be. All right, so let's get out that graphing calculator. Figure this out. Now, to get to the 2-SAMP F test, we press the stat key right here. Then we go over to test using our right arrow key. Use the down arrow key to find the menu item that says 2-SAMP F test. Here it is, 2-SAMP F test. That's 2-sample F test. Press enter there. Now, if data is highlighted, you want to use your right arrow key to put the cursor on top of stats and then press enter to highlight it. Okay. So now, S sub x1, that's the first sample standard deviation. That's the larger of these two. That's that 5.31. We enter that. And N1 would be the sample size that has the standard deviation of 5.31. In this case, it's 30. And then S sub x2 would be the other, 5.19. And then N2 is the sample size related to that sample standard deviation of 5.19. That's going to be 30. And then sigma 1 is either going to be not equal to or less than or greater than. If you look at your alternative hypothesis, it's not equal to. So you want the cursor on top of the not equal to sigma 2, press enter to highlight that. And then use your down arrow key to highlight the word calculate, put the cursor on top of calculate, press enter. And here we go. What's on top is the alternative hypothesis here. This is your F test statistic. That's your p-value. So that F test statistic to 2 decimal places will be 1.05. Okay. All right, so with this, it is important that S1 be the larger of your 2 standard deviations. And then S2 would be the smaller of the 2. But do make sure that you enter the correct sample sizes that are related to the larger standard deviation and the sample size related to the smaller. Okay, now step number 6 is the p-value. Again, we're using a TI-84 plus calculator. I'm going to bring that calculator back up here because as you can see, underneath the capital letter F, there's lowercase p, that's your p-value. And the p-value to 3 decimal places will be 0.903. okay? 0.903. Okay, I don't know why it went out on me like that, but let me show you, yeah. Okay, so there's the p-value to 3 decimal places, 0.903. All right, so that's step number 6. Now, step number 7 is the decision rule. And that's this. If your p-value is less than or equal to alpha, you want to reject the null hypothesis. Otherwise, fail to reject the null hypothesis. So my p-value is 0.903. That alpha level was 0.05. You can see that 0.903 is much greater than 0.05. In fact, your p-value, that's exactly the probability of getting a test statistic as extreme as the one that we obtained from our summary statistics. And here, a p-value of 0.903, that means we have a 90% chance of getting a test statistic that extreme, okay? And it's greater than 0.05, so we need to fail to reject the null hypothesis. And there's an old saying that says, if the p-value is high, then no one must fly. Yeah, that p-value is real high. And then step number 8 is our conclusion using simple non-technical terms. The claim was the null hypothesis, and we failed to reject that null hypothesis. Okay, so we're not going to be able. Well, there's no sufficient evidence to reject the claim. So we have to say this: there is not sufficient evidence to warrant rejection of the claim that the variation of maximal skull breadths in 4000 BC is the same as the variation in AD 150. So that's our 8-step hypothesis procedure for doing 2 variances. All right, here's another example. Okay, here words were displayed on a computer screen with background colors of red and blue. Results from scores on a test of word recall are given below. Use a 0.05 significance level to test the claim that the samples are from populations with the same standard deviation. Assume that both samples are independent, simple random samples from populations having normal distributions. Does the background color appear to have an effect on the variation of word recall scores? Okay, so here's our sample data. All right, I'm going to identify S1 first. That's the larger of these two standard deviations, which is in this case 5.99. And for S2 will have to be 5.46. That would mean for the 5.99, which is the larger of the two, N1 will have to be 34. So N1, let me rewrite that. N1 has to be 34. And for the 5.46, N2 will have to be 36. Okay. All right, so now step number 1 is the original claim in symbolic form. We're testing the claim that the samples are from populations with the same standard deviation. That means sigma 1 will have to be equal to sigma 2. Because, of course, same standard deviation, that means they got to be equal. And then step number 2 is the opposite of the original claim. Or the opposite of equal to will have to be not equal to. So sigma 1 will not be equal to sigma 2. And then step number 3 is your null and alternative hypothesis. Well, the null has the equal sign in it. So this will be sigma 1 equals to sigma 2, which is also the claim. The alternative has the not equal to in it. Sigma 1 does not equal to sigma 2. And now step number 4. The level of significance. Again, we're using a 0.05 significance level. So the alpha is equal to 0.05. And then step number 5 is where we use our graphing calculator to find the F-test statistic. So I'll just say here, using a TI-84 plus calculator, we're going to find out what F is. Okay, press Stat key, go over to Test. Drop down using a down arrow key to find 2SAMP F-test, which is right here. Then press Enter. Stat should already be highlighted. Okay, so now press Enter. No, that's use your down arrow key for that. S1, S of X1, that's the larger of the two standard deviations, which is in this case 5.99. And N1 with 5.99 is your sample size of 34. And then S2, S of X2, that's going to be 5.46. And its sample size with that would be 36. All right, now let's look at our alternative hypothesis. That's not equal to. So here, not equal to needs to be highlighted. So press Enter there, and then go all the way down to calculate. Press Enter. The F is your test statistic. To 2 decimal places, that would be 1.20. Okay, so that's our F test statistic there, 1.20. And then step number 6, again, we're going to use the TI-84 plus calculator. To get our p-value. So here, there's our p-value right there. To 3 decimal places, that will be 0.5. Let's see here. The 9 is here, the third number after the decimal point. This 5 will make that 9 from 89 to 90, so it'll be 0.590. Okay. That means the probability of getting a test value, a test statistic as extreme as the one obtained from our summary statistics will be about 59%. And then step number 7 is our decision rule, which is if the p-value is less than or equal to alpha, you want to reject the null hypothesis. So in this case here, that p-value was 0.590, and that alpha load was 0.05. As you can see, 0.590 is greater than 0.05. So that means we need to fail to reject the null hypothesis, because it didn't satisfy our decision rule. And then step number 8 is the conclusion in simple non-technical terms. The claim was the null hypothesis. We failed to reject that null hypothesis, meaning that there is not sufficient evidence to warrant rejection of the claim. So we can say here that there is not sufficient evidence to warrant rejection of the claim that the samples, I'm just rewriting what that claim is. The samples are from populations with the same standard deviation. Okay. Now, the other part of the question is, does the background color appear to have an effect on the variation of word recall scores? And pretty much, since we failed to reject the null hypothesis, that answer would definitely be no. Meaning that the variation of word recall scores appear to be the same when the color is changed. Okay, and that's simply because we failed to reject that null hypothesis that that the populations had the same standard deviation. Okay, here's the last example in this video. Say this: the accompanying table gives results from a study of words spoken in a day by men and women. Assume that both samples are independent, simple random samples from populations having normal distributions. Use a 0.05 significance level to test the claim that the numbers of words spoken in a day by men vary more than the numbers of words spoken in a day by women. And here's that data set. Well, not data set, the summary statistics here. Okay. Now, S1 will have to be the larger of the two standard deviations. In this case, it's this number, 8,632.8. And S2 will have to be the other, 7,301.4. And for S1, which is this number, N1 will have to be 186. And then for the 7301.4, this will be N2, 208. Okay. Because S1 is always going to be the larger of the two standard deviations, and N1 will be the sample size that has the larger sample standard deviation. Okay. So now, step number 1 is to write the original claim in symbolic form. In this case here, we're testing a claim that the number of words spoken in a day by men. I'm letting the subscript of 1 be for men and the subscript for 2 be for women. That means, now write out original claim. That means this. The standard deviation for the men, which is sigma 1, has to be greater than, because it says vary more than, so that means greater than sigma 2. Okay. And now step number 2 is the opposite of the original claim. And that's this. The opposite of greater than will be less than or equal to. So sigma 1 will be less than or equal to sigma 2. And then step number 3 will be writing our null and alternative hypothesis. The null always has the equal sign. So it has to be sigma 1 equaling to sigma 2. And the alternative has either the less than, greater than, or not equal to. This one has strictly greater than. So this will be sigma 1 greater than sigma 2. That's the claim. And then step number 4 is your level of significance. That's the alpha level, 0.05. And now step number 5 is where we use our TI-84 plus calculator to get our F-test statistic. And we'll also use that to find the p-value as well. So here, we go to stack, press the stack key, right arrow over to test, use your down arrow key to find 2SAMP F-test, which is right here. Stack should always be highlighted because we're only using summary statistics. Use your down arrow key to enter S1. That's 8,632.8. And then its sample size, 186. Then go to S2 to enter the other sample standard deviation, 7301.4. And N2 is that sample size related to S2, 208. Now this time, let's look at our alternative hypothesis. It says greater than, okay? So to highlight greater than, we use our right arrow key to put the cursor on top of greater than sigma 2. Press enter, because that needs to be highlighted. And then use your down arrow key to go all the way down to calculate. Press enter. So now we know what our F-test statistic is. To two decimal places, this will be 1 point. Well, that 7 will make 39 of 40. So it'll be 1.40 as your F-test statistic. And also we can use that output to get our p-value. So you're using a TI-84 plus calculator. The p-value is, let's say, to 3 decimal places, this will be, I know that's 0.009, but that 5 will make the 9 1 0. So it'll be 0.010. That's your p-value. And now step number 7 is the decision rule. That's this. If your p-value is less than or equal to alpha, you're going to reject the null hypothesis. So here the p-value was 0.010. Your alpha low was 0.05. Well, 0.010 is less than 0.05. Here it's strictly less than. And it does satisfy the decision rule, so that means I need to reject the null hypothesis. And then finally, step number 8 is the conclusion. Well, we rejected the null hypothesis and the claim was the alternative, so that means that we have sufficient evidence to support the claim. So we can start by saying that there is sufficient evidence to support the claim. That. And then we write what that claim is. The number of words spoken in a day by men vary more than the number of words spoken in a day by women. Okay. Right. So pretty much that's the 8-step procedure that we use to test a claim about two variances here. All right. So this does conclude this video in section 9.4 dealing with two variances or standard deviation using the hypothesis testing procedure.